So we'll move to the next session. The next session is about soil improvement. And then I'll pass it to Chu.
Okay,
All
good.
right.
Thank you. The slicer, this one. Okay, fine. Forward, this one. Forward, this one. Huh? Okay, good afternoon. James K. Mitchell, he's truly a giant. The brief tangential encountering with him 30 plus years ago makes such a huge impact on my life. Indeed, it changed the course of my life to a certain extent. Jim is definitely a first-class researcher, but as what Jonathan Blake just now pointed out, he's also a practitioner, especially in the area of ground improvement, CPT, etc., ground characterization, etc. To me, he's a great engineer. He's here to solve the real-life problem. The greatness of Jim, in what I see, is he can perfectly integrate the research and the practical reality and solve the practical problem beautifully. For example, like I mentioned, in soil improvement, CPT, etc. problem. Now, hence, instead of going into detail on some technical aspects, I rather want to demonstrate what James' legacy, James' teaching, that all of us, presumably we're all James' students, one way or another, that we inherited from him. How did we pass on? I'm a professor in a local university in Singapore, to our students, and finally pass on to the industry. So bear with me, I have many slides, but pictures speak for itself. Don't worry, I can finish in 20 minutes. So, okay, I was asked to talk on the topic on ground soil improvement. Yes, that's a topic I love. That's a topic I inherited from James, and I came from Singapore. I was graduated from Singapore. I was recruited by the local university, National University of Singapore, to be the lecturer in preparation, and sent over to top university in the world to be trained and then returned to Singapore. My head of department, Lee Sing Lip, some of you may know him, some of you may not know him, because he's a structural professor. He graduated from Berkeley. So to him, there's only one top school in the world in engineering. That's Berkeley. So when they recruited me, he said, you must go to Berkeley. In fact, at that time, I already received, before I talked to the head, I already received the confirmation from another university, even with housing arrangement done. My head of department canceled that, tear that, what was the form? I-94 form away, visa away. Said, you must go to Berkeley. And he personally wrote to, I think, Harry Seed and Jim, to introduce me and ask them to take me in. So I remember the first day, then subsequently I came and took the one-year master and then moved on to PhD. Now, I remember the meeting I had with Jim, on the first meeting on what should I work on. At that time, Jim tried to understand the place where I came from, Singapore, tried to understand the development stage of Singapore. And knowing that I would return to Singapore, he said, hey, Sun Ho, you should, by the way, he called me Chewy. I don't know why, who started. I think it's Rose who started it. You should think of things that is more impactful to Singapore. Yes, I'll be doing research in university, but I'll be teaching many more engineers in Singapore that will impact the society, impact the industry better. So he asked me, what do I want to work on? Actually, being Asian, we normally don't express our opinion in front of our superior. So I have to very politely say, no, please, Prof. I didn't even call him Professor Jim. I just said, Prof, please recommend, please introduce something to me. He said, I generally don't decide for students. But for your case, let me pause. And then he decided, hey, why don't you work on some new area called soil improvement using geosynthetic? I expressed gratitude and very happy to say, yes, thank you, I'll start working on that. 30 years later, I have to tell the truth. Actually, I didn't understand what he's saying. I went home and checked out dictionary, geosynthetic. I brought along Oxford Advanced Learner Dictionary. I think this you should. In Singapore, I bought that and bring along. I cannot find this word. Then I later realized Sorry, Rudy. It's a French guy who came out this word. Huh? Anyway, wow, that started my whole research. Yes, I researched on the geosynthetic, research on ground improvement, and I'm sure we have a great man like Ed and Zornberg is going to continue to talk on that. But let me share with you my experience with Jim, okay? Now, of course, the first, I should mention that he is, to me, he's really the number one man in soil, in ground improvement. He's the number one in ground improvement. I remember his state-of-the-art paper in 1981, Stockholm Conference. To me, it's still state-of-the-art today. It was 1981. To me, still today, of course, in between, there's a lot of development, but still a lot of basic principles, a lot of key concerns he rightfully pointed out. Now, I take a look. By the way, I have that state-of-the-art paper, and I just, to my horror, I check out the table of content of that particular conference, 1981. You see, these are all the state-of-the-art paper. Everybody is writing about 20, 30, 20, 12, 20 pages. Jim paper is 56 pages. 56 pages. I don't know how many PhD students was asked to review, helping him to summarize things. But he wrote 56 pages, and every words are so profound and so important. Anyway, that is his paper, State-of-the-Art Soil Improvement, 1981. And not only that, he really spent time, like some of the senior have said, read through every references and make some comment, find something good or wrong about it. He has a list of references, 191 of them, in total of 6 pages in double column format. Amazing, right? Now, what I learned from Mitchell, most important legacy and teaching is combining 3 aspects: practical problem solving, fundamental of soil behavior. Of course, we heard about his 4th edition of books. By the way, his book is must read for my graduate student, but unfortunately so expensive and most of them didn't buy. Previously, there was a cheaper version, but now no more. But anyway, we'll see how to, but definitely it's one of the very important books that graduate students in Singapore must be aware of. And of course, I should also say that Mitchell here and there always stressed about innovation. He's quite far-sighted. He talked about, somebody was asking, Mr. Chairman asking, what do you think Jim will work on now? I think one of the things will be on sustainability. I read one of his latest paper. I think Virginia Poly tech student, the colleague may correct me if I'm wrong. One of his latest papers is on carbon footprint for ground improvement. I thought it was very interesting. All right, anyway, so I'm going to share with you the 4 aspects that has affected me, and being his student, I follow his footsteps and affected my student and the industry in Malaysia and Singapore. Very quickly, I want to highlight 4 aspects which some of you are very familiar with: cement treatment for soft clay, innovative PVD using electro-osmosis. Probably, I think Albert has spoken a lot on that. Geosynthetic soil improvement using poorly draining soil. I think Zornberg may talk about more of that. Freezing technique in tropical country. Let's move very fast. Okay, we can skip this one. Well, I know all this story telling you jet grouting, deep cement mixing become a norm in Singapore, or of course in Hong Kong as well. When I first returned to Singapore, not many people know about this technique, but now it become a norm. Not only that, because we have a lot of underground construction, we have thick layer of soft clay, we have a lot of mega project, like I'm going to show you airport, things like that, that really need ground improvement. And not only that, I should proudly announce to everybody that XRD, SEM become common day knowledge among geotech engineers in Singapore now, thanks to me and other Mitchell students, that we try to tell people that, hey, you want to know real soil behavior, especially clay, you must know what Mitchell is holding on here. It was Mitchell holding on what Mitchell holding on here, which is here, the model of the clay mineral. All right, and these are my standard lecture note material, telling students all the clay, different type of clay mineral in a model form and in a schematic diagram form. And we start to realize that to really properly understand the behavior of cemented, treated soft clay, you really need to understand this. So, so as I say, this is an XRD picture. By the way, this is not from Berkeley. This is from Singapore, from one of my consulting jobs. right? And today it's common that we can do this. This is the one untreated Singapore marine clay. You can see mainly it's a quartz because we do have the silk-sized particle, eulite, kaolinite. But after treatment with cement, you can see that all kaolinite clay seems to disappear and form into CSH, calcium silicate hydrate, as well as the 50%, 30%, things like that. Now, we did, my student did a little summary, and in one very easy way to illustrate to people that if you're untreated clay, by the time you treat it with cement, kaolinite is the one that will be transformed to CSH first, and subsequently maybe eulite. But a lot of time we'll find in Singapore actually only kaolinite being transformed. So that will probably explain why certain part of Singapore clay are more effective treated with cement because there are more percent of kaolinite. The other part of Singapore or the other part in Malaysia, the other part in Bangkok, the clay are less kaolinite, more eulite. All right, so that will probably explain very well. So that's what on the thing. These are, again, some standard, Berkeley student, nothing new, right? This is not the best picture. You see a better picture from Mitchell, but this in Singapore. This is my pictures. First thing I went to Singapore is to convince my head of department buy a scanning electron microscope and buy a X-ray diffraction machine. And we use it in a lot of our consulting job and explain to people how clay structure change by adding all this. We even buy the expensive mercury intrusion proximetry and then to determine the particle size. So this is a very interesting picture to explain to students or to industry the particle size distribution when you add it with cement, actually effectively you can increase the larger portion. Similarly, the pore size. By the way, in Singapore, we follow the British standard. We plot particle distribution this way. In US, I think you plot this way, where particle size big and small. So anyway, that illustrates the increase in particle size and the pore size due to cement treatment to the different degree of cementation. We also move into incineration ash, and you can see with the incineration ash, the SCM feature will be quite different when you add with SCM with that. Okay, now talk about innovation. One of the things that I'm proud to announce to everybody is my student and me also get into the mechanism of doing the jet grouting. And then we develop a bigger diameter jet grout pile. In the market Singapore, typical piles are up to about 2.6 meter, typically 2.6 meter, about 8 feet. But with my involvement, my student involvement, we managed to change it to 4.3 to 5 meters, 16 feet. And with that, what Mitchell teach me, look beyond, these are all the test results, I can skip this. Look beyond soil mechanics. Someone was saying that he learned chemistry, I have to learn mechanical engineering stuff to realize that the effectiveness of jet grouting depends on the nozzle. And one of the important things is the nozzle shape, nozzle size, and the kinetic energy, how to shoot far so they can cut the soil. So therefore, we even invent the testing. You can see that this is the conventional jet grouting. The jet energy can disperse at a short distance. Whether the sonic jet that I developed together with my student, the concentrated energy can disperse very, very far distance. This is a special paper that I can put right in front here. And indeed, you can, let me see, you can run a short video. This is they're just starting. You can see, yeah, if it's a good jet, you see that you will hit the target here with a good pressure. Normal jet will not impose any pressure, so therefore, it bigger, smaller diameter. Okay, let's move on to second topics. Oops. Okay, second topic is on EO. Well, you can skip all this. I think all the theory, Albert nicely shows all the complicated equation. But in Singapore, follow Jim's concept, see where it can apply on the field now. So therefore, we apply on the field. And we managed to find one place. But before that, let me show the end result. This is the end result showing people that this is the normal surcharge without PVD. This is the one with PVD. PVD is a prefabricated vertical drain. Or in US, we call it weak drain. Weak drain, and this is the one with electric weak drain. You can see it's much faster. So by introducing electric current into the ground, you're driving water molecule through electroosmosis, move to cathode, and you can easily pump it out. So that will effectively achieve the consolidation without adding too much of without needing of the surcharge on top, okay? And also time is fast. And we do a few trials in Singapore, and this is our reclamation project. You can see just look like normal PVD, but you look at it carefully, the drain itself, we have to connect with the wires. These are all the copper wires. There are two different colors. One is anode, one is cathode, and then we run the test. To cut the story short, these are my poor PhD students, have to risk their life to measure the potential gradient when the power are supplied. Although we tell them this is at your own risk, huh? Anyway, safe. I was there myself too. All right, I just cut short to summarize one of the key maybe summarize into this graph that will show you that I'm plotting, instead of settlement, I'm plotting the strength in gain versus time. This is a conventional PVD calculation, and with the electric vertical drain under EO, you can see them move on blue line and move here. When you apply about 12 days, 14 days, you can achieve the strength equivalent to about 200 days of the normal consolidation time. So with that, you really speed up the consolidation. Of course, that translates into money saving and et cetera, et cetera. But of course, you pay for the higher material cost for the EVD, you pay for the cost of applying the current. All right? But anyway, that is one step forward. Third, quick question is, of course, in my PhD topic is on reinforced soil wall. I should say that I'm honored to join the esteemed super team of Adib, Makam Jaber, Gary Smerman not here, and of course, Jorge Zornberg. And I forget to mention Collins, James Collins. Of course, James Collins was before I arrived at Berkeley. These are the team of people that started the work on soil reinforcement. And of course, we helped to compile the FHWA guide, things like that. Now, I must mention that at that time, the FHWA guide is only allowing sandy soil, which is freely draining field, to be applied. When we returned to Singapore, I realized that actually for all the projects that we do not have free draining sand. We do not have clean sand. But on the other hand, we have a lot of silty sand, clay silt, sandy silt. We got residual soil, which is a mixture of sand and silt and clay to a certain extent. So they're not good draining, but can we use them? So therefore, I started my research on that poorly draining field. And of course, I understand that Zornberg, of course, subsequently become big man on that, about same time of that, okay? So I carried a lot of large pull-out tests, centrifugal testing, et cetera, But one of the important things I've done is I'm collaborating with Dr. Philippe Damas from Polyfeld French, of course, subsequently a company bought over by others, to develop a new type of geotextile product that take into account not only reinforcement, but also in-plane drainage. So in short, a kind of reinforcement, you have a high-strength yarn, woven yarn that take care of the reinforcement aspect, but you also have the thick, non-woven base, which provide the in-plane water drainage. So with that, water can come in during heavy rain and flow along this non-woven geotextile, serve as a very thin horizontal drain, and it worked well for us. So I have to do a large pull-out box. At that time, that's when I was young. And then we conduct a lot of tests on this, and using different type of material. This is PEC material. We also conduct on GeoGrid as well as other products. And you can see this is a typical result, showing you that the residual soil is not perfect, but nevertheless, it's still pretty good pull-out capacity, but the pull-out capacity will drop by almost 20% when it's soaked with water. So that engineer has to be aware of. So you did extra factor of safety to take care of this soaking effect. But of course, at the same time, this horizontal drainage may help to dissipate part of this. Okay, now, due to the short of time, I just want to show you a few things to illustrate to you. Yeah, this is the kind of soil that we have. It's definitely not sand because we use a sheep foot compactor, which is what Jim taught us in the class. This is only for clay soil, and we did that. All right, and that's how we build all the wall with different facing. I can skip all this. I just will show you that how high we build all this wall with this residual soil, and the movement we monitor upon completion of the project, total height, even up to about 40 meters, still about less than 20 mm. If we stagger it, we kind of stagger it, so it's good. Sometimes we like it more green, so the facing we also want it to end up with green, like this. Of course, we can wrap with some of the natural jute fiber as a facing component, right? And then with that, you can see how well you can, this is a facing component, and with time, you can see that turn into green. So this is the complete wall in September 2005, and about next 5-6 months, September, so for 4 or 5 months later, it's as good as this, and forever stay like this. Green, nice, sustainable. Last but not least, this one I can skip. Last but not least, I just have 2 slides. Singapore is a hot place. Our average room temperatures all day, all years, all day long and all year round is about 26 to 30, 80 Fahrenheit to 87 Fahrenheit, something like that. This is all day, every day and the whole throughout the year, and this year after year. Year after year means you still see a bit of upward trend, but still in the 80s. So in short, Singapore is hot, very hot. So the question, will freezing method that Mitchell teach in the class, will it be able to apply in Singapore? When I teach that, all my engineers laugh, say, no, never use it. So after 3 years of my teaching, remember, last story, After 3 years of my teaching, one day, big company, big government contractor came to me. They're constructing an MRT station at Woodland, which has a layer of thin sand layer and water still gushing in. So they cannot proceed with the work. So they asked me, what's the solution? I remember what Mitchell said, freezing. So I said, why don't you freeze it? They say, wait, you must be a young, permanent head damage. They walk out, they storm out my door. But 3 months later, they find no other solution. So indeed, they did that. So they used freezing to freeze the loose sand, okay, and work beautifully. All right, that was a private job. I'm the consultant. Now, subsequently, that was early 2000. Then, subsequently, there's a big project. This is not by me, by somebody else. My students, actually my students' colleagues, realized, hey, we need to strengthen. This is downtown. I show the picture. This is the last pictures. This is the existing, we call MRT, Mass Rapid Transit, which is your BART, your subway. So we're existing BART line here, and want to build 2 new ones across it. And this is downtown, so a lot of building here with a lot of piles. So we really can't do any better. So finally they say, to avoid soil movement, these are soft clay. So they say, hey, why don't do freezing? So can you see frozen wall left and right for them to build this tunnel, lower tunnel, and then subsequently make it here to build the upper tunnel. Without going to any numbers, ladies and gentlemen, what I learned from Mitchell, I hope I correctly pass on to my student and actually went out to the industry in Singapore. Today, SCM, XRD is a known knowledge in Singapore. Today, soil reinforcement with the poorly draining soil, with the proper design, is the known knowledge in Singapore. And today, even freezing in the hot temperature is possible. And it was, or you were, successfully done in 2 of the jobs. That is Mitchell's legacy. So finally, I just want to say, to me, he is an excellent teacher. He's an excellent researcher, a caring mentor to me. And don't forget, he was an outstanding engineer. And may God bless his family continuously, today and forever. God bless everybody. Thank you.
Now we have Professor Ed Kavazanjian.
All right. So one of the, I guess, disadvantages of being towards the back end of the program is a lot of the really profound things I was going to say have been said by others before me. But it just goes to show the influence that Jim Mitchell has had on many of us. So I want to talk about his contributions to soil improvement, which are many. But before I do, I wanted to start, like some of the other speakers, with a personal note. So this is me in 1978, more hair, a lot less weight. But the first time I met Jim was 5 years before, in 1973. And I was starting my graduate study, my master's program, but it wasn't at Berkeley, it was at MIT. And I was one of 3 new graduate students for Professor Lamb, and we were summoned on that first day to a meeting in a classroom with a bunch of other people, none of whom I knew. And Lamb went ahead and described the 3 projects that he was going to assign the new research assistants to. And as he described one on a performance of a surcharge in Aventura, Florida, the guy sitting next to me, who I didn't know from Adam, leaned over to me and said, "You know, I know a little something about that project. I think it's going to be very interesting." So Lamb finished describing the projects and then asked who wanted to work on what project. And the only piece of information I had was this stranger sitting next to me who said, "That's going to be an interesting project." So my hand went up. That person was Jim Mitchell. And Jim was at MIT on sabbatical, writing his soil behavior book. And for the next 9 months, I got to work with Jim on the Aventura preload. We used all kinds of prediction methods for settlement and strength gain. It was, if you know, Professor Lamb had these 3 classes of prediction. Class A, Class B, Class C. Class A was you made the prediction before the project was built. And in Lamb's mind, it was the only true prediction. And this was a Class A prediction. We were running one of these fancy new finite element programs that included consolidation, which was trend setting at the time, believe it or not. I worked with Jim for 9 months, played squash with Jim for 9 months. And I think many of you have heard that Jim was a fierce competitor, but so was I. So we had some great squash matches. And at the end of that 9 months, he was going back to Berkeley. I said to him, "You know, Professor Mitchell, I had applied to the master's program at Berkeley, and I was accepted, but I wasn't offered any financial aid, so I stayed at MIT." And Jim said to me, "Well, you might want to apply to the program again." And so the master's program was a 2-year program at MIT. The next year I reapplied to Berkeley and was admitted, and that was the beginning of my long-term relationship with Jim. So inconsequential, what at the time seemed like an inconsequential comment by a complete stranger sitting next to me led to 50 years of friendship and collaboration. Excuse me. So when you talk about, when we think about Jim, typically the first thing you think about is soil behavior. But if you look at his contributions, you look at his bibliography, you'll see probably the biggest chunk of papers is on soil improvement. And there's probably not, or there were very few soil improvement techniques that Jim didn't work on. Maybe one of the ones missing from this list was the project I worked on with him at MIT, which was a surcharge. But you know, I'm sure he was involved in many surcharges in his consulting work. But Jim's contributions are myriad, and I could read the list, but I don't think it's worth the time. But it was not just techniques, improvement techniques, but state-of-the-art reports, performance reports on the performance of improved soils and earthquakes. And you've already heard mentioned one of the last things he worked upon was sustainability. Go on. So I think, was it Rick who mentioned that after Jim graduated from MIT, he spent 3 years in the Army. And maybe he spent some of that time blowing up bridges, I don't know. But I do know he spent a lot of that time at the Waterways Experiment Station. And perhaps the first paper that he published after his PhD thesis was on work he did on soil improvement at Waterways. So by the time this paper was published, he was at Berkeley, but the work was done at Wes. And Jim was the lead author of this paper on a review and evaluation of soil cement pavements. So ground improvement, his first foray into ground improvement. He moved on to UC Berkeley, and he continued to work on compaction. You've heard a lot of comments about how compaction is fundamental to soil improvement. This is another example of Jim's work on soil improvement. So 1961, by 1961, he was at Berkeley. He continued to work on soil improvement, compaction, in this case, lime-stabilized expansive clay. And, you know, a lot of the topics he worked on early in his career, he continued to work on through his career. We heard earlier today about the work on compacted lime-stabilized clay and the development of ettringite and swelling in those clays, which came later in his career. One of Jim's hallmarks was his penchant for collaboration, and Jim was a wonderful collaborator, very gracious with his time if you were collaborating with him, and with credit for the work that was done, giving his coworkers credit. Here's some of the early work he did with collaborators at Berkeley who he worked with throughout his career. Harry Seed, Clarence Chan, Carl Monosmith, who I know Jim had a very long relationship with. So this is early in his UCB career when he started this history of collaboration with his colleagues. We've heard comments earlier about fundamental principles and Jim's focus on fundamental principles of soil behavior. In fact, ground improvement is an extension of soil behavior. If you want to design an effective and efficient ground improvement program, you need to know how soil behaves. So a lot of the relationships we make on compacted clays, which we take for granted now, the effect of compaction energy, the effect of compaction moisture content on the structure of clay, those were fundamental breakthroughs that Jim Mitchell developed in the early 1960s. And this paper by Mitchell, Hooper, and Campanella is one I still have the students in my soil improvement class read. It's a fantastic paper about the relationship between compaction energy, moisture content, and the behavior of compacted clays. We've heard about Jim's work on coupled flow phenomena and its contributions to soil improvement. And there's a wonderful diagram in soil behavior. I hope it's still in the 4th edition. I know it was in the 1st, 2nd, and 3rd edition. And it's a 4x4 matrix of the 4 conduction phenomena: fluid, thermal, chemical, and heat transfer. And on the diagonal are the direct flow relationships: Darcy's law, Ohm's law, Fourier. But the off-diagonal terms are the coupling terms of how electrical flow is coupled with fluid flow, and how chemical flow is coupled with fluid flow and with electrical flow. And again, when I teach soil improvement, I dedicate an entire slide in most of the lecture talking about that coupling. And we've also heard Don Gray mention, one of Jim's first PhD students at Berkeley. And so this is some of the work that Jim did with Don Gray on electroosmosis. And again, he returned to working on electroosmosis throughout his career. 1976, Jim organized probably the first conference on soil improvement at UC Berkeley. And it was a 5-day symposium. The intent was to raise money. Berkeley, or the U.S. National Society, had just been awarded the 1985 International Conference on Soil Mechanics. And Harry Seed had this program to raise money for it. This was the first part of it. And this was an all-star team of the who's who in geotechnical engineering in the U.S., plus a few international participants thrown in: Jim Mitchell, Don Gray. I can see it better from here. I think my voice can carry far enough. Marshall Thompson, Carl Monosmith, Stan Johnson at the Corps of Engineers, Harry Seed, Chuck Ladd, Les Bromwell, and Anwar Wisa from MIT. Literally who's who of geotechnical engineers, 35 papers on soil improvement. I still have these 2 thick blue binders with the 35 papers, and I still have occasion on particular types of soil improvement to go back to that binder and look at the contributions from these outstanding geotechnical engineers to soil improvement. We also heard in the last presentation, well, in several presentations, about the first state-of-the-art report on soil improvement that Jim authored for the 1981 Soil Mechanics Conference. That was the first of several. Jim was involved in several state-of-the-art, state-of-the-practice summaries of soil improvement, but this was the first comprehensive summary in a single place of soil improvement techniques. Jim also recognized the importance of performance assessments. It's one thing to predict the densification that occurs in practice. It's another to demonstrate that densification was effective, in this case, at mitigating soil liquefaction potential. And so it wasn't just the theory, it wasn't just the field technique, but it was also the performance of the engineered structure that Jim focused on. Physical model testing. So Jim did not hesitate to use new technology. We heard Robert Leong talked earlier where his PhD thesis was on centrifuge testing. It was a joint project. I was teaching at Stanford at the time, and Jim and I had this joint project. When we were planning the proposal, Harry Seed sat in on a meeting. And Harry was a skeptic. He didn't think this new technique that the Brits had developed of centrifuge testing really had any role in geotechnical engineering. And so Jim carefully explained to Harry what we were relying on the centrifuge testing for. And Harry got up and said, "Thank you, Jim. I now understand the value of centrifuge testing." And he left the room. So this is some later work that he did, and I don't know exactly what Jorge is going to talk about, but this was Jorge's dissertation. He continued to innovate throughout his career. We might hear about this a little bit later from Russell Green, looking at an energy method for predicting liquefaction, or the potential for liquefaction in soils. And then he continued to show leadership throughout his career. There was a committee on geological and geotechnical engineering and new millennium, opportunities for research and technical innovation, a National Academy committee that Jim participated on, and it identified 4 areas in geotechnical engineering for the 21st century, for innovation in the 21st century, including biotechnologies, which is something near and dear to my heart. I appreciated the comment I think Scott made that if Jim was alive today, he'd be working on geotechnical engineering. In fact, for my engineering research center, Jim was on the science advisory board for the first 5 years of the center as we launched our efforts into developing these new methods. And one of the seminal papers on biological contributions in geotechnical engineering was written by Carlos Santamarina and Jim Mitchell, and has this wonderful diagram comparing particle size, pore throat size, and the range in which microorganisms can penetrate soil and contribute to soil improvement. And then finally, sustainability. So Jim constantly changed with the time. He was constantly looking at what the key issues were in that time and making contributions to those issues. And so one of the last papers that I could find that Jim was a co-author of was on energy and carbon assessments, embodied carbon assessments of ground improvement. And it was a 2-part paper with the theory and then a working model and examples. So those are some examples of the many ways in which Jim has contributed to soil improvement throughout his career. We've heard, to me, Jim is an exemplar for all of us on how to conduct ourselves professionally, personally. He was a Boy Scout leader. He played in a jazz band. He was a renowned geotechnical engineer, an innovator, an educator. Most importantly, to me, he was my dear friend, and I really miss him. Thank you.
So our third speaker in soil improvement is Professor Jorge Zornberg.
Good afternoon. What a privilege to be here honoring Jim Mitchell with such a distinguished audience. All of us influenced by Jim. I'm going to follow on the topic of soil improvement, but I'm specifically going to talk about geosynthetics. And I would consider a broad interpretation of soil improvement because geosynthetics is really mixing soil with a non-soil material. In a sense, one way or the other, we are modifying the way that the soil behaves. And so that's why one of the words in here is geosynthetics. But I'm going to mention, and I'm going to explain why, I'm going to talk about addressing the reactive nature of our geotechnical discipline using geosynthetics. So first, let me tell you about my first exposure to geosynthetics, and was here at Berkeley. So I came here and I considered myself a numerical modeler. I consider myself a constitutive modeler. And suddenly, I was exposed to go to Missoula, Montana, and probably mingling with people that have never heard someone with an accent, and working on a very important instrumentation project, very much related to the topic that you mentioned. And again, this is a major reinforced salt slope that was monitored. And the key in this particular project was that it was decomposed granite, and essentially it didn't meet what we now would call free draining material. So the idea was to use exactly the same material from polyfelt that you mentioned about, and the idea was to capitalize on the dual function of these geosynthetic. One was reinforcement, and the other in-plane drainage. I also worked on the, and as Ed mentioned, I also worked with Jim and with Nick on the use of, on the understanding of reinforced salt slopes, but in a centrifuge test. And I had the privilege of going to UC Davis very regularly and worked in your marvelous small centrifuge. I love that centrifuge. And that's where I have my first speeding ticket. That was in UC Davis. So I was driving at 25. Say, why are you stopping me? No, the speed limit is 20, so okay. So, but it was a great experience, and essentially we learned that our design methods, for the most part, work well. And we understood that limit equilibrium really works, and we could see, we could not bring this big structure to failure. This monitored structure was to understand the behavior of reinforced salt structures under working stress conditions. But then we learned also how geosynthetic reinforced salt structures could work at failure. And yes, our tools work. And peak, what governs? Peak shear strength, another residual shear strength that is used in Europe works. And those are the type of items that I did work during my PhD, my first exposure to geosynthetics. And that's an area that I continue working on. I would say that my areas that I work the most are two. One is geosynthetics in different ways, and the other is unsaturated flow. And the reason that I came about unsaturated flow was after my PhD, I worked with a geosyntech with Ed. And, well, they're putting me in a big proposal for the OII Superfund site for the evapotranspirative cover systems. And I said, I'm a geosynthetics guy. Why are you going to put me in a proposal for doing a non-geosynthetic cover system? Well, the idea that it was a big message saying that a geosynthetic expert was saying that the right cover at this place was a non-geosynthetic solution. But after I went back to academia, and here we have why I'm going to be talking about the reactive geotechnical discipline. This is 1999. I had just joined the University of Colorado Boulder. This is the same event in Falls de Iguazu that Rodrigo mentioned. And I was just getting my ropes together on what to focus on as a faculty member. And here's Jim giving a keynote lecture. Fantastic work. And the topic was, and I can read it, education in the geotechnical discipline. What has been driven this field? And I was eager to get to see what he was saying. And if you can see there, a big and important aspect was what were the drivers in the geotechnical field. And to my surprise, Jim, when talking about the drivers, and he mentioned Carl Terzaghi and how uncertainty matters and how each geotechnical project is unique. But then he said something that at the time, I would consider a offense, or potentially by some. And this is what he said about the geotechnical discipline. He said that although many professors might be reluctant to admit it, education in geotechnical engineering has been largely reactive. That is, experience, practice, and the introduction of new construction technologies have often led the theory and complete understanding. So, and this was daunting, and it sounded right. We know how to do geotechnical projects, but in many, many cases, we know that our solution will work. We may not know exactly why. And then came, and many of you referred to his book. And I'm going to go to the second edition because it's the one that I have with Jim's handwriting. And I'm looking forward to the fourth edition. But I'm also going to highlight something that is very, very relevant, and many of you have already mentioned. And Jim mentioned that in many cases, a knowledge of how a soil behaves is sufficient for selection of a geotechnical solution of a geotechnical problem. And most previous books on soil mechanics emphasize this aspect of behavior. There are cases, however, where a complete understanding of why certain soils behave as they do is necessary. And this is an important aspect, oh, here I'm reading better, and can provide the important solution that is to be provided. So this was kind of clicked. I already knew that Jim was working on the why, but he was working on the why in a field that really needed that why. So the uncertainty and the uniqueness of geotechnical engineering is great, but there is a lot of need of why. So one thing that may have not been said is I believe that Jim was a great strategist because he found a field where there was a significant need of explaining why things behave as they do, and that's what he focused on. So with my PhD and many of your PhDs, essentially if this is the world of knowledge in geotechnical engineering, with our PhD we can push and create a dent in our knowledge, in the state of the knowledge in geotechnical engineering. That's my PhD. However, Jim was able to create a significant increase the boundaries of our knowledge in geotechnical engineering because he was focusing, I could kind of disagree that he was working in too many different areas. I think that he worked on one, and that one was why the soil behaves as it does. Okay, so now within the topic of why things work as they do, I'm going to take you to the area of geosynthetics. And in a sense, this is also an area where there is a lot of need of understanding of why geosynthetics work as they do. So what I'm going to show you is not necessarily research activities in which Jim was involved, but research activities, and I'm not even going to talk about the research. I'm going to talk about, because a lot of this why was to real practical problems, real practical questions. There was a lot of fundamental. All his work was fundamental, but fundamental that was needed for real impact in our profession. So I'm going to walk you through, not through the actual research, but through some case studies that motivate understanding why geosynthetics work the way that they do. And the first project that I'm going to take you is in an area where geosynthetics is growing significantly is in the mining sector. So I'm going to take you to a mining project near Cusco in Peru. And essentially, this is the Las Bambas copper mine. This is one of the largest copper mines in the world. And the need in here, when something is needed in mining, is needed now. They needed rapid relocation of water from a reservoir for continued mining operations. And the solution was to build a high-capacity canal, and it was done using geocells with concrete infill. So here it is, the mine, and you can appreciate these are the mining operation facilities, and you can see the tailings dam, you can see an open pit over there on your right. But what I'm going to call your attention is to the reservoir of fresh water and the smaller reservoir where the water was really needed. So the idea is it was a need for rapid conveyance of water from this location to this second location. And the solution was particularly challenging, and there is a good understanding of that this solution does work. Geocells provide an alternative to reinforced concrete in this case, but with shrinkage in a very, very controlled manner. And I'm going to come back to the quantification of the leakage through this. But in this particular case, it was such a deep excavation cut that it needed essentially vertical walls, and geocells are not ready for that. So in this particular project, the solution was to join a geogrid anchored on the surface with a geocell. And the other second important problem is now we have a geocell system in the canal, but now it's how do you place concrete in here? So another unusual aspect was the placement of the concrete was done using shotcrete instead of the commonly applied fresh concrete. So this was an example in which the significance was the use of shotcrete, the use of a geogrid instead of steel stakes to get the geocell in place. But the main message is why does it work? Why does it work? Well, there was a need to quantify. We know that it works, but why? Well, it has something to do with the fact that if you control the leakage through small cracks, the leakage is proportional not to the thickness, not to the square of the thickness, but to the cube of the thickness of the crack. So we'd rather have a significant number of small cracks in our concrete structure than potentially the significant cracks that may occur if we let the concrete by itself or with joints. In addition to that, it was necessary to quantify what was the extraction capacity of the geocells from the concrete infill under significant water flows. Okay, that was one example. Let me tell you another example. In this case, soft foundation soils. Typically, when we think of geosynthetics, we think of retaining structures. We do not think of soft soils, soft foundation soils. Well, that's not true. So I'm going to take you now to Turkey, to the Kavazanjian embankment. And essentially, the solution in this particular case was to adopt a technique that is the use, and by the way, at this particular location, the problem was also seismic. Many particular important problems. It had to be placed, an embankment had to be constructed underwater. There were 14 meters of soft clays, and it was in a highly seismic area. And the solution was to use what is called geotextile encased columns. Geotextile encased columns have been here for a while, and they are particularly good when stone columns are not suitable. Here we're talking about an undrained shear strength on the order of 15 kPa, 300 PSF. So with that very low shear strength, the gravel doesn't sustain by itself. So not only you need the encasement in order to maintain the integrity of the system, but also you take the opportunity to confine the gravel laterally and add strength to your system. And that is what the solution was. And this is the setting, essentially a new reservoir that divided essentially a city in two. So they needed a bridge, but the bridge had to go over 14 meters of very soft soil. It was already underwater. So this was the first placement that I understand that it was of this operation underwater. And essentially we're talking about a 22 meter high, 430 meters long, 430 meters long embankment that was constructed below the water. And it was designed with a design acceleration of 40% acceleration of gravity. Stone columns a study by colleagues demonstrated that stone columns could not maintain their capacity, their bearing capacity, their capacity after an earthquake, but a geotextile encased column could. And here is a view of the construction of the underwater system, installation of the geotextile encased columns. And here is on the order of 12,000, and that is correct. So it's 12,000 geotextile encased columns were the foundation of this embankment. So what is the significance here? The significance is that the project illustrates the ability on using geosynthetics in a project that typically we do not think on them, which is foundations, and foundations on very soft soils. It was successfully undertook underwater. And what is that we need to know that we know that it works, but why it works? Well, we still needed to understand what was the relevance of the hoop stresses in how much are they going to be maintained, how much of that load is transferred by shear, and the interaction with a nearby. We're talking about columns that are 1.7 meters each center to center apart. So, and what you see here on your right are stone column models, but built on transparent clay. And through this, we were able to understand that the validity of some of the design assumptions that are being made currently for these type of projects. All right, so let me take you to another example in which we need to understand why. And this is for bridge design. I'm going to take you to Colorado, near Denver, and south of Denver. And the project in here is the Founders Meadow Bridge Abutment. And the important aspect that the Colorado DOT wanted to achieve was they wanted to get rid of the bump at the end of the bridge. That was a big motivation. They also wanted an expeditious construction. And the solution was what ended up being the very first, at least the first in a major highway, the very first, and it has different names, but I'm going to call it the first load-carrying geosynthetic reinforced bridge abutment, rather than using deep foundations, which is a typical way in which the girders, the load of the girders is transferred to the foundation soil. So let me just to clarify, if you're not familiar with this technology, I think that is extremely promising, but let me clarify the differences between a retaining wall, a geosynthetic reinforced wall, and here a bridge abutment that is a geosynthetic, this is a GMSC wall, geosynthetic reinforced bridge abutment, which this is, if you drive by here in California or in Texas, this is what you're going to see. You're going to see many, many geosynthetic reinforced abutments, but they carry the load of the approaching road. These are retaining walls. We design them as retaining walls. But the load, and that's why we have the bump at the end of the bridge. So the approaching road settles, and the bridge doesn't settle, and that's when you have a bump, when you get into the bridge and you have another bump. And I was surprised in learning how much money goes into the maintenance and accidents that occur because of this bump at the end of the bridge. Instead, what this construction was essentially this. It was not a reinforced wall. It was not a reinforced foundation. It was both. So this is what we call a load-carrying geosynthetic reinforced bridge abutment. And it was successfully constructed, but this was 1998. So now we're talking about over 25 years, and we'll revisit this is 1998 during construction. The big motivation was getting rid of the bump at the end of the bridge. It was also because it didn't require deep foundations, it was very expeditious to construct. It was easier to sequence the construction of the different lanes. And, well, let's revisit it. A year and a half ago, here's another view of the very same bridge, extremely well-performing, and guess what? No indication of any incipient bump at the end of the bridge. So what is the significance of this project? Well, this is the first bridge constructed on a major highway. It has been done in the US before, but for very small structures. And the monitoring results, one of the monitoring results, they demonstrate very, very good performance. So why does it work? What was needed? We know that it works. Well, there were many questions. There were questions, okay, this is a concentrated load, and this is a polymeric material. Will we have time-dependent problems? I can tell you now, no, we don't. What about the load? There is a significant emphasis nowadays in design trying to accommodate or to account for vertical spacing, and particularly close vertical spacing. And essentially what you see on your right is a big pull-out box, not with one geosynthetic, but with three. Essentially, we see what is the impact of vertical spacing on the interaction of these different geosynthetic materials. I'm going to take you now to another topic, and we're going to see geosynthetics to address the challenges of unsaturated soils. Unsaturated soils, that's not for geosynthetics, but yes, I'm going to take you now to the Daniel Boone Bridge in Missouri. And there was a need to build this structure, but there was a problem. The water table was very high. So capillarity would do its job, and a common base material has fines, and if the fines get moist, essentially we compromise significantly the structural capacity of the bridge. So what was the solution in this particular case? To adopt geosynthetics that can fight the unsaturated flow, that can fight capillarity, that can still, believe it or not, if you're familiar with unsaturated soil, essentially drains do not drain under unsaturated conditions. Drains drain once the contact between the soil and the drain becomes saturated. If not, drains do not drain. The only way to make a drain drain under unsaturated conditions is adding suction. So that's what these new products, some would call them intelligent geosynthetics, are doing. So here is a view of the location, Interstate 64. Essentially, there was an existing bridge. There was a second bridge. Now they needed a third bridge, essentially in order to attend the capacity. And there was a solution, very expensive solution, that it was to have such a clean drainage material that essentially would work as a capillary barrier and would not allow the moisture to advance into the regular base. And instead, the solution was to add a regular base material, but with this wicking geosynthetic. Here you see a view of the placement of the geosynthetic with wicking capabilities that would essentially have the moisture migrating from the high water table into the interface with the base, but then it would migrate under suction laterally. And here, even during construction, this was already observed that the wicking drains were working. So what is the significance? Well, the adoption of geosynthetics with enhanced lateral drainage avoided the use of very expensive, needed to be transported hauled from very far away, and no pavement distresses have been identified since its construction. Now, the key is why? Why do they work? What is the trick? There are many aspects to be sorted out, but this is the idea. So we do have the wicking. We're talking about very, very small, literally, capillary tubes. And where are those tubes? Well, these are really grooves within the fibers themselves. So think about it. When we think of a geotextile, and yes, they have pores, but that's not the water that we're talking about. The geotextile has pores. That's not the pores where the water is conveyed. Typically, this textile has yarns, a family of fibers. But in each one of these yarns, that's not the moisture migration that we're talking about. What we're really talking about, and here's the cross-sections of the actual fibers, is the migration of water through these capillary tubes. And in pavement engineering and under capillarity, we're talking about very, very small flows. The flow that we're talking about is somewhere on the order, and when I say report this in liters, I know that many of you could not relate to it, is 3 bottles of wine per foot per day. That's the small flow that we are talking about, and that makes a significant difference. I'm going to take you to the last one. In this case is problematic soils. More specifically, where I am, the problem is expansive clays. In the north, the problem is volumetric changes due to frost heave susceptible soils. So I'm going to take you to the expansive clay soils. Milam County in Texas. What was the problem? The detrimental effect caused by expansive clays. And this is a real problem that was poorly understood until very recently. The problem here, very often we attribute the distress to traffic, has nothing to do with traffic. Some would call these environmental loads. And the idea is that during the dry season, the shoulders of the road that is paved, so the moisture infiltrates through the shoulders or desiccates through the shoulders. So during the dry season, the shoulders desiccate and settle in relation to the center line. And that's when you're going to see the distress, that is the fingerprint of expansive clays that are longitudinal cracks. During the wet season, the shoulders will heave first in relation to the center line. And the cracks could even close. But the cracks are already there, and the migration of water has already started, and the degradation process has already started. So how was this solved? Essentially, there are different ways in which geosynthetics can work, but the one that I'm going to show you is a geosynthetic that was used to stabilize the base of the material. This is a real problem. This is close to my home, East Austin. This is what you see in a low-volume road. And these longitudinal cracks have nothing to do with traffic. Actually, because it's close to home, we monitored the profile, how much, and this is a not particularly extreme drying event. We just monitor how much, and these are relative movements, how much the shoulders move in relation to the center line. And we're talking about 20 millimeters in a regular year. We're talking about an inch that goes up and down, and when it goes down, that's when you're going to see the cracks. So how was this? One example, and this my hand is off for the Department of Transportation. When they see that there is a potential for a solution, they create test sections. And in this particular case, I'm going to show you there's some evidence that come from test sections. One is a control section, a typical low-volume road without geosynthetics. Another test section, the same road, the same weather conditions, the same traffic conditions, the same soils. We know the soils change, but with a geosynthetics. And even more daring, the same section, but now with a reduced base and compensated for a geosynthetic. And these are some observations. So this is the control section, no longitudinal cracks. And this is this is not the control section. This is the section 1. This is the section with the reinforcement, no longitudinal cracks. Here is the control section with longitudinal cracks. Same cross-section, same traffic, same subgrade, same weather conditions, same drainage conditions, longitudinal cracks. Even you do not see the longitudinal cracks, even when you try to capitalize, because this geosynthetics or this solution has been promoted with rightfully so, that they provide additional, also some benefits to the traffic loads. And even when reducing the base, one of the potential benefits, we do not see the longitudinal cracks. So lesson, the geosynthetics prevented the development of longitudinal cracks. But why do they work? Well, that's when we come. So the significance is field evidence has shown that basal reinforcement stabilization precludes the development of longitudinal cracks. And why does it work? Well, it's a long story, but I'm going to tell you that is the interaction between the geosynthetic, in this particular case, for example, a geogrid with the base that essentially maintains the integrity of the base. When you have a longitudinal cracks, it's because there was a strain concentration that triggers the crack. So this is not preventing the vertical movements. The vertical movements will occur. What will not be triggered are the longitudinal cracks. That's why it works as it does. So Final remarks. In these case studies, my intention was to show solutions that even though Jim may have not been working on these particular projects, they were inspired by trying to not only understand how this solution would work, but why it works as it does. So we have seen why geocells with concrete infill will work in mining projects for water conveyance, and geotextile encased columns will provide foundation bearing capacity to very soft soils, and how the bump at the end of the bridge can be addressed by a special type or unique type of design, how even we can have flow under unsaturated conditions when using what we call wicking geosynthetics, and how we can deal with problematic soils such as expansive clays. Final remarks. Although geosynthetics are now a well-established technology in our portfolio of geotechnical engineering solutions, they are particularly well-suited because we know what properties, if we understand the mechanisms, we know the properties that we can tap into. We just need to know what the mechanisms are, and we will be able to deliver the properties. And I would say that with continued inspiration from Professor Mitchell, the solutions involving geosynthetics have facilitated understanding not only of how and if the system would work, but also why they behave as they do. So some 30 years ago, this is July 1994, I graduated in December, but Jim was already in Virginia Tech, so I took the opportunity of the commencement ceremony to be hooded. This is a view of 30 years ago, and this is myself, my daughter, my very pregnant wife at the time in front of the Hearst Mining building. And on behalf of my family and a significant number of academic grandchildren at the University of Texas at Austin, I thank you for your attention.